how exactly do we look inside a beating, working human heart without, so much as lifting a scalpel? For decades, this was literally a medical impossibility. The heart was essentially a locked box. You could really only get in through major surgery, or maybe by just listening blindly through a stethoscope. But today we can actually watch the heart's valves open and close in real time. We can measure the exact speed of blood rushing through its chambers, and even pinpoint microscopic areas of muscle damage. So what's the secret here? We're turning sound into sight.
Hello, and welcome to This Explainer. I am absolutely thrilled you're joining us. Today, we're going to completely demystify the echocardiogram. That's the standard, non-invasive ultrasound of the heart. We're going to break down some pretty complex medical physics and cardiac anatomy into a really clear step-by-step journey. And by the end of this, you won't just know what an echo is, you're going to understand exactly how medical professionals use it to decode the hidden mechanics of the human heart. So, here is our roadmap for today. First, we'll look at the power of sound waves. Second, windows to the heart. Third, measuring a healthy heart. Fourth, diagnosing heart failure. And finally, spotting damage and disease. Let's just jump right in. Section 1. The power of sound waves. From abstract physics to cardiac mechanics. Okay, let's dive into this. To really understand the heart, we first have to understand our main tool, the ultrasound probe or transducer. Its power rests on something called the piezoelectric effect. Honestly, it sounds like magic, but it's pure physics. Inside the probe, there are these special crystals. When you pass an electrical current through them, they vibrate. They rapidly create these mechanical oscillations. And those oscillations, they're ultrasound waves, sound pitched so incredibly high, well over 20,000 hertz, that our human ears literally cannot hear it. The probe sends these sound waves into the body, they bounce off the tissues of the heart, and when they return, those exact same crystals translate the mechanical echo back into an electrical signal that the computer turns into an image. It's a real game changer. Now, to actually control that image, we have to manipulate the components of sound. Velocity is constant, so in human soft tissue, sound travels at exactly 1,540 meters per second. But frequency and wavelength are inversely related. And this is a critical balancing act for whoever is performing the echo. If you use a high-frequency probe, the wavelength is shorter. This gives you these beautiful, high-resolution images, but the sound can't penetrate very deep, which is absolutely perfect for examining children. But for a larger adult, where the heart is sitting deeper in the chest, you have to use a lower-frequency probe. You basically sacrifice a little bit of that pristine image resolution to get the longer wavelengths you need to penetrate deep into the body. But an echo machine doesn't just show us static tissue, right? It shows us moving blood. And to do that, it relies on a phenomenon you all know. Have you ever noticed how a car horn or a siren changes pitch as it drives by? It sounds a lot higher as it approaches you and then lower as it speeds away. Well, that right there is the Doppler effect. The echo machine uses that exact same principle, but instead of a car, it's bouncing sound waves off microscopic, moving red blood cells. By measuring the shift in frequency between the sound waves sent out and the echo received back, the computer can instantly calculate both the speed and the direction of blood flowing through the heart's valves. All right, moving on to Section 2, Windows to the Heart. Seeing the heart from different angles. So the main challenge with echoing the heart is that it's protected by a cage of ribs and air-filled lungs, which unfortunately completely block ultrasound signals. So the sonographer has to hunt down specific acoustic windows where the heart touches the chest wall directly. These standard windows include the left parasternal, which is right next to the breastbone, the apical, right at the bottom tip of the heart, and the subcostal, looking up from just under the rib cage. By placing the probe at these specific windows and carefully tilting it from the base of the heart to the apex, a technique we actually call bread loafing, we get multiple, standardized cross-sectional slices of the heart structures. Once we have a really clear structural window, we turn on color flow mapping to make immediate sense of all that Doppler data. The machine actually paints the blood flow in colors right over the black and white structural image. And the golden rule to remember here is BART, blue away, red towards. It's brilliant in its simplicity. When blood is flowing away from the ultrasound probe, it's painted blue. When it's flowing toward the probe, it's painted red. And this brilliantly illustrates exactly what the blood is doing at any given millisecond. The brighter the red or blue, the higher the velocity. But what if the blood isn't flowing smoothly? What if it's turbulent, just violently crashing through a narrowed, diseased valve? Well, the machine paints that high-variance, turbulent flow in bright green. Instantly, a splash of green on the screen alerts our medical detective to a serious problem. Section 3. Measuring a healthy heart. Establishing the baseline. You know, before we can even spot disease, we absolutely have to know what normal looks like. We measure wall thickness, chamber dimensions, and most importantly, pumping efficiency. And I'll tell you, the undisputed king of all cardiac metrics is the left ventricular ejection fraction, which normally sits right between 50 and 75%. The ejection fraction is literally just the percentage of blood that gets squeezed out of that chamber with every single heartbeat. A healthy heart doesn't empty completely, it ejects between 50 and 75% of its volume. If this number starts to drop, that's our very first major clue that the heart is failing. Section 4. Diagnosing heart failure. When the mechanics break down. Now, heart failure doesn't actually mean the heart has just stopped. It means the mechanics have broken down and the heart can no longer meet the body's demands. Echocardiography reveals that heart failure generally comes in two distinct flavors. On one side, we have systolic dysfunction. This is a failure of the squeeze. The heart walls have become stretched out thin and really weak, so the ejection fraction drops well below normal. On the other side, we have diastolic dysfunction. This is a failure of relaxation. The heart's walls have become thick, stiff, and completely rigid. The heart might squeeze just fine, but because it's so stiff, it can't relax to let enough blood fill the chamber in the first place. And as they say, you can't pump what you don't have. Often, these dysfunctions are caused by cardiomyopathies, which literally translates to heart muscle diseases. Just imagine you're the medical detective looking at the scan. If you see a massive, dilated, globular-shaped heart with thin walls that barely even move, a condition called global hypokinesia, you're looking at dilated cardiomyopathy. If instead you see a small, squeezed cavity with thick walls that look unnaturally bright and speckled, you found restrictive cardiomyopathy, which is usually caused by abnormal proteins infiltrating the muscle. And what if you see this massive, asymmetrical thickening of just the middle wall dividing the heart? It causes these vigorous contractions that actually block the blood from leaving the heart? Well, that's hypertrophic cardiomyopathy. So that's 3 very distinct physical clues, all captured entirely by sound waves. Which brings us to Section 5, Spotting Damage and Disease, the final detective clues. The absolute most common condition an echo evaluates is coronary artery disease. When the arteries feeding the heart get blocked, the heart muscle starts to starve, and its movement changes dramatically. We actually classify these abnormal wall motions on a scale. Hypokinesia means reduced inward motion. Akinesia means the tissue is totally paralyzed. There's just no inward motion at all. And dyskinesia, that means the tissue is so badly damaged it actually expands outward paradoxically during a heartbeat. Over time, that dead tissue turns into bright, thinned out, fibrous scar tissue. So the crucial point is this. Because we know exactly which coronary artery feeds which specific wall of the heart, simply by watching which wall stops moving on the scan, an echocardiographer can pinpoint exactly which artery is blocked. It's truly amazing. Now, coronary artery disease is essentially a timeline, right? A narrative arc of destruction if it's left untreated. It begins with ischemia, which is a temporary lack of oxygen where the wall motion gets sluggish, but it's still reversible. If the blockage persists, it becomes an infarction, a full-blown heart attack. The tissue dies and scars over. And finally, that dead tissue undergoes what we call remodeling. The sheer pressure of the blood inside the heart can cause that thinned-out dead wall to bulge outward into a balloon-like sac, and that is what we call an aneurysm. But, and this is absolutely critical, there is a massive life or death difference in the types of aneurysms the echo detects. A true left ventricular aneurysm has a wide neck and is made of tough, scarred heart muscle. It bulges outward, sure, but it rarely ruptures. Now, what's really interesting and honestly terrifying is the pseudoaneurysm. This happens when the heart muscle actually tears completely open, but the bleeding is temporarily contained by the thin outer sac surrounding the heart, called the pericardium. It has a very narrow neck and forms a globular pouch. A pseudoaneurysm is literally a ticking time bomb. It is highly prone to fatal rupture at any moment and requires immediate emergency surgery. Catching that precise difference on an echo, that saves lives. From the piezoelectric PC crystals vibrating in the probe, to the Doppler shifts painting the blood blue and red, all the way down to spotting the precise microscopic clues of a failing heart, echocardiography is just an absolute triumph of modern medicine. We've learned to literally listen to the heart's mechanics, to see its structure, and it leaves us with an incredible thought to ponder. If simple sound waves can reveal all this about a beating, working heart today, what hidden mysteries of the human body will ultrasound decode tomorrow? Thanks so much for joining me for this explainer. Keep learning, keep looking deeper, and I'll catch you next time.
Hope you liked our video. Share this information with your loved ones. And don't forget to subscribe to our channel. Thank you.